All right, welcome. Today, we're diving into a real scientific detective story, a journey to crack one of the biggest mysteries of all, the atom. We're going to follow the clues, piece by piece, to figure out what our world is actually made of. Okay, so let's just start with a totally wild idea. What if everything around you, the chair you're in, the screen you're looking at, even you, is 99.9% empty space? I know, it sounds completely nuts, but that's the central mystery we are here to solve today.
So where do you even begin with a case this big? Well, like any good detective story, you start at the very beginning. Our first person of interest isn't really a person, it's an idea, the very first concept of the atom.
Way back in 1803, a scientist named John Dalton came up with this theory. Basically, he pictured atoms as these tiny, solid, unbreakable spheres, like microscopic billiard balls. And for his time, it was a totally brilliant model. But, as we're about to see, some new evidence was about to blow the case wide open.
So this is basically our case file, our roadmap for this whole investigation. In just over a century, our idea of the atom went from a simple little ball to something way, way weirder. Let's follow the evidence trail. Now remember, Dalton's whole idea was that the atom was the smallest thing possible, the end of the road. But oh no, our detective story is just getting started, because scientists were about to find the first major crack in the case. And here it is. In 1897, J.J. Thomson discovered something smaller living inside the atom, a tiny negatively charged particle called the electron. I mean, this was a huge deal. It proved that atoms weren't indivisible after all. They actually had parts. So to try and explain this, Thomson came up with what we now famously call the plum pudding model. Okay, so picture this. You've got this ball of positively charged pudding, and stuck inside are these negatively charged electrons, kind of like raisins or plums. This became the leading theory, but spoiler alert, it wasn't going to last long. Okay, and this is where our investigation takes a really dramatic turn, because the next piece of evidence didn't just poke holes in the plum pudding model, it completely blew it out of the water.
Right, so in 1909, the scientist, Ernest Rutherford, decides to put the plum pudding model to the test. He sets up this experiment where he fires a stream of tiny, positive particles at a sheet of gold foil that's super, super thin. Now, based on the old model, what do you think he was expecting? He thought they'd just sail right through, like shooting a BB gun through a cloud of mist.
Yeah, that's not what happened. Not even close. Look at that last point. Most of the particles did go through, sure, but a tiny, tiny fraction. We're talking like 1 in 8,000, bounced right back. I mean, Rutherford himself said it was as incredible as if you fired a 15-inch cannonball at a piece of tissue paper and it came bouncing right back at you. Just unbelievable. So what could possibly explain this? Well, there was only one logical conclusion. All of the atom's positive charge, and almost all of its mass, had to be crammed into this impossibly tiny, dense core right at the center. He called it the nucleus. And the rest of the atom? Well, that's where we get our answer to that crazy question from the beginning. It was almost entirely empty space. You can see right here just how massive a shift this was. Science went from this idea of a soft, mushy atom to one with a hard, dense center and electrons orbiting super far away. It wasn't just a small correction, it was a total revolution in how we understood reality. So, discovering the nucleus was absolutely the key that cracked the case wide open. But the picture wasn't quite complete yet. A few more puzzle pieces still needed to fall into place. And here are the last two big ones. First up, Niels Bohr figured out that electrons weren't just buzzing around all over the place. Nope, they were neatly organized in these fixed energy levels, or shells. And then James Chadwick found the final missing suspect hiding out in the nucleus, the neutron, a particle with mass but zero charge. So here's our final cast of characters. You've got the positive proton, the neutral neutron, and the negative electron. And just look at the mass column. Protons and neutrons are our heavy hitters, each with a mass of about 1. But the electron? Its mass is so tiny, it's practically negligible. And that's exactly why the nucleus contains pretty much all the mass of the atom. So now that we have our complete model of the atom, we can actually use it to decode any element in the universe. And to do that, you just need to know two really important numbers. First is the atomic number. This one's easy. It's just the number of protons. Think of it as the atom's social security number, its ID card. It defines what the element is. If an atom has 6 protons, it is always carbon. Always. Then you have the mass number, which is just the total count of everything in the nucleus, protons plus neutrons. And using those two numbers, we can figure out everything else. So if you want to find out how many neutrons an atom has, it's just some super simple subtraction. Seriously, you just take the total number of things in the nucleus, that's the mass number, and you subtract the number of protons, the atomic number. Let's try it out. Let's say we have an atom of copper. It's got a mass number of 63 and an atomic number of 29. So the question is, how many neutrons does it have? Well, you just take the big number, 63, subtract the smaller number, 29, and what do you get? 34. 34 neutrons. It's that easy.
Okay, but this is where it gets really interesting. What happens if you keep the number of protons the same, but you change the number of neutrons? Well, then you get an isotope. Isotopes are basically just different flavors of the same element. They've got the exact same number of protons, so they're still the same element chemically, but they weigh different amounts because they're packing a different number of neutrons.
And the classic example, the perfect one to look at, is hydrogen. Every single hydrogen atom in the entire universe has exactly 1 proton. That is what makes it hydrogen. But its neutron count can change. And here they are, the whole hydrogen family. Most hydrogen out there, it has 0 neutrons, plain old hydrogen 1. But then you've got deuterium, which has 1 neutron, and the even rarer tritium, which has 2. See? Same element, same single proton, just different weights. That's the whole idea of an isotope. So there you have it. We followed the clues all the way from a simple, solid ball to this incredible, complex solar system in miniature. And we solved the mystery of the empty space. We've cracked the atom. But you know, every solved case just opens up new questions. What forces hold that tiny, packed nucleus together against all odds? What other secrets is it hiding? Well, that's a detective story for another time.